Let's start. So before I start, I would like to thank the organizers and the sponsors of the conference and everyone else who's helping with the event. This is an amazing conference. The stage is just amazing at the expo level. It's just so awesome to see. This is my first time at NDC. I haven't attended any NDC event. I know, I'm probably like the one person who hasn't attended NDC conferences. All my friends, I talk to them, they always speak about how awesome these conferences are. So this is a privilege, really, to attend the conference. Apart from that, I'm really jet lagged. I just flew in yesterday. I live in Vancouver, BC, Canada. And so this is not, if I zone out in the middle of the talk, please wake me up. Just stay with me on this one. I know it's 3 p.m., and it's this kind of the time when you need a coffee. So hopefully this talk is entertaining enough for you all. So today we're going to talk about taming infrastructure workflow at scale with HashiCorp's Terraform. So the idea is to go through what has changed in the last 25, 30 years in infrastructure in terms of how we deliver infrastructure, and then kind of go through the workflows associated with that delivery. And then kind of we'll dive into what Terraform is and open up all the layers. And then at the end, I have a few live demos. If the demo gods are with me, we'll do the demos on conference Wi-Fi, and we'll see how that goes. So a bit of a context, if this clicker works. Bit of a context, my name is Mishra. I'm a developer advocate at HashiCorp. Prior to HashiCorp, I've spent most of my time, past 4 or 5 years, working on the infrastructure problems as an operator, as a SRE. I've done a bunch of open source tools in that space to kind of solve those problems. And my passion is really distributed systems and microservice delivery platforms. And now, as a developer advocate at HashiCorp, I kind of get to focus on all 6 of our popular tools. They're all open source as well. So who's actually heard of HashiCorp? At least, there should be a few hands. OK, good. So that's good. I'm doing my job, which is awesome. So HashiCorp, we're less known for our company name. We're more known for our tools. We have 6 distinct tools spanning 3 of these spaces: the provision space, the secure space, and the run space. So the idea is with HashiCorp is we focus on application delivery, and this is how we look at it. In the provisioning space, you might use Vagrant, which is for building developer environments, and then Packer for building server images. This might be a Google image or a Amazon AMI or even Docker containers. Terraform today, we're going to talk about it and see how that works. It is an infrastructure as code tool that lets you provision resources for different infrastructures. So it could be a cloud provider or your on-prem data center. Then Vault comes in the security layer. It kind of helps with the secrets management problem and the secret sprawl that we see in organizations. And then at the runtime layer, we have Nomad, which is our application scheduler. This is a general-purpose scheduler. It lets you schedule containerized applications like Docker, Rocket containers, and also non-containerized applications like Java applications, standalone binaries, and things like that. And then Console is kind of special. It is a service discovery tool. It kind of spans all the 3 spaces. It kind of connects them all together. But today, we'll only focus on Terraform. And then we have a bunch of enterprise products. So before we get into kind of talk about Terraform, let's kind of go through this journey together in terms of what the evolution has been for the last 25, 30 years. So if you go back 30 years, right, we have this one server that we have. This might be in a basement or in a closet, right? This might be a mainframe. Mainframes were really popular back then. They were really good at doing one thing. They would run this one application really well, really efficiently. And that worked out. And this is where we kind of saw the rise of mainframes, and they dominated this space. And then, we figured that we need to do more work, and we need to be a little bit more efficient. So we added a bunch more servers. At this point, the servers started to shrink and become smaller, and mainframes are kind of disappearing from mainstream. But companies like Dell are coming in, and they're dominating this space. So these servers would be, networked together and racked up together. We would figure out cooling and things like that, power, and how we want to do networking between them. But what was interesting was, in terms of applications, we were still doing one-to-one mapping. So we would assign one app to one of these servers, the Java app to the server that has more memory, that it can kind of dominate the whole server or something. So we kind of still did the one-to-one mapping. And then what happened is, if you take another last 15 years or whatever, we saw a rise in programming languages like Python and Ruby, And this is where we kind of saw running multiple applications on the same server kind of became a necessity. And this is where you saw like tools like virtualenv become really popular, in which you wanted to run multiple Python versions on the same server and things like that. And then 10 years ago, we saw this like really interesting, hypervisor wars, in which Zen versus KVM became a debate, and Zen kind of dominated a bunch of stuff, and you saw VMware come in, and that dominated the enterprise data center space, and which is super interesting. But most interestingly, we actually for the first time, got something called virtual machines, which were the first disposable like dynamic artifact. So before, we were waiting months for these servers to be provisioned and networked, and like your data operations team would figure out how to install, what OS to install, and things like that. And now, with virtual machines, for the first time, we were able to get these things provisioned within hours rather than months, and this was pretty awesome. And then now, if you see 5 years ago, we are in the era of this thing called containers. I'll try to use less of the word container. But yeah, so the idea is that you have like Docker and Rocket containers, which is an immutable artifact. You can spin these up really fast and spin them down pretty fast as well. But the data center complexity is rising. At this point, you have virtual machines and containers kind of running side by side. In some cases, you're running these containers inside the virtual machines. You're also running some bare metal databases. You're also running in the cloud. And then we enter in this like era of like the cloud native applications. Again, like the idea here is that this application is built for the cloud. It might be using some services like Route 53 or Azure's DNS or DNS Simple or something like that for DNS, and they might be using some managed databases like Azure's Cosmos DB or Google's Spanner or Amazon's RDS instances. But the idea is that you're realizing that you're running less and less of your own infrastructure and then using most of these cloud providers' applications. So that's basically like kind of the complexity that has come now with the variety of workloads that we run in our data centers today. And to make the problem even more difficult, you might be running multiple of these data centers, and that might be one for one US region or one for Europe region or something like that. And they might have their own complexity when you kind of unlayer them, right? So there is a rise in complexity. There's a variety of applications that are running. Even like functions as a service has become a thing now. So you're running that side by side. All the other stuff that you're running. Now, in terms of workflows, a lot has changed again. And this was just the infrastructure evolution, but the workflow evolution is even more interesting. So before, what we did is we actually bought things. So we went to a vendor, we put in an order. In months, like 6 months later, we would get these things delivered at our data center. We would unpack it. We would then rack them up, figure out all the cooling, power, and stuff like that, right? And then this would take months, right? And then you had like the DC ops team or DC data center operations team that would come in and kind of like actually install some operating system on these machines and basically figure out all the networking, all the routing, and things like that. And then these machines, to make them useful, they would pass it on to the product and engineering team, and these would include like your IT operators or system admins that would install some hypervisor that would get these machines usable, and now you can run VMs on it. And that was the process. And so, the product teams, they actually offset like 8 months. So when they were building a new product, they would say, okay, it's at least going to take 8 months before we get new infrastructure and everything ready for us to kind of use. And that was the life cycle, and that was the norm, and everyone was OK with it, right? But now, if you kind of only focus on, let's say, the buying phase, right? What is buying today? You just sign up for a cloud provider account. It takes you probably a minute or something, and you have all these compute resources available to you right away. You might choose Amazon or Azure or Google or whatever else you want. Oracle Cloud, yes, that's a thing as well. Oracle has a cloud. So that is basically what buying is today, right? In terms of provisioning, we saw this really interesting kind of like people come together and build like really cool provisioning stuff. So the idea here was to kind of bring in the config management systems like Chef, Ansible, Puppet, and things like that. And these would let you provision a set of servers within hours. This could be installing like all the Java dependencies, Python dependencies, and things like that, and make these servers ready to install your application on. And maybe in some cases, orchestrate deployments and things like that. So yeah, that was the provisioning side. And this would take hours. And then on the update and destroy, basically, that was a cloud provider call, API call away. So now you can actually do an API call and kill 100 servers if you wanted to. Before, you had to physically go to the data center in some cases and maybe unplug the power cable or something, which hopefully no one does. But yeah, that's the case. And then on top of that, you need all these other things to kind of get your data center, to get your applications out there today. You need some kind of VCS system. It could be GitHub or GitHub Enterprise or GitLab or Bitbucket. You might be using a cluster orchestrator like Kubernetes, Nomad, or Mesos. You might be using Docker on the side, just standalone Docker. You might be using Jenkins. You need some CI/CD stuff. There's all these other things that you need in order to get infrastructure out or applications out today. And the most popular way we do this today in startups and mid-sized companies are this really interesting, really innovative workflow called console-driven workflow, in which you go to the data providers like Console or whatever and say launch instance, and then you say next, you select, OK, I need Ubuntu 16.04 or something. Then you say next, and then you say, OK, allow SSH from the internet, and then you say allow port 80 through the internet, and that's it, and you launch instances. And you get a bunch of web servers or whatever. And then to even make the problem more complex, you SSH in, you run some apt-get commands. In some cases, you might be just installing the default version of Java. In some cases, you do the Oracle way, and then do some symlinking and do some Java, figure out the Java home and things like that, and then your applications are ready. So this is awesome for startups because they only want to focus on applications. They don't care about scale at this point. They don't foresee these problems at all, right? And it works for them because they are really focused on product and making their company successful. Now let's say you're lucky enough to be in that 0.1% in which you actually hit a certain scale where you need more compute. You need more web servers, let's say. So what do we do now? So this is where this cloud provider's amazing feature comes into hand. You say you right-click and you say launch more like this. This is I've used it as well. I've made this mistake before too. So you can launch more like this, and you can keep scaling up until a certain server comes up, and then you realize there's a huge drift between the one server that's the latest copy of the original server and the original server, because so many people have come in and snowflake changes between these servers, and that's how it is, right? So this is how we do things today. On the CLI side, there's a CLI-driven workflow, which is you use the cloud providers CLI tools, like AWS's AWS CLI tool, or Azure's AZ tool, or Google's G-Cloud tool, and you just spin up instances. You write some bash scripts to make it scalable and collaborate on it. You would actually wrap these around Python and Bash and Perl scripts and share that in your company. And then you realize that certain scripts work for certain servers, the other ones don't work for this one network, and there's all these other problems. So it doesn't give you a cohesive way to kind of do these things. Oh yeah, that's the Azure CLI. It looks pretty pretty. The whole slide is the logo, and then the rest, all the commands couldn't fit in because the logo is so big. They think about everything really well, which is pretty awesome. So as an operator, entering this kind of area in last 6, 7 years, I was really confused, right? I was why did we make such decisions in which we've come to a place where we're running such hybrid stuff. It was so easy before. You had your own data centers, so you could go in and kind of see these machines, touch these machines, feel these machines. Now you can't do any of that. You have no control over your data or your network or how you provision storage and the I/O performance and things like that. And so why did we actually change? I always ask this question to myself, and the answer is pretty straightforward, actually. Because we wanted to deliver things at a faster pace, right? This is pretty obvious. We need to get applications out from really day one, start focus on our business and things like that. And the other one was another less obvious one, which is we need to deliver applications at scale. And there's a bunch of buzzwords here, but the idea being that startups today and mid-sized companies today, they want Google scale infrastructure from day one. So when they sign up for Google or Amazon or Azure, they want to be able to kind of see that success story of Instagram and Facebook, that they will get to that 10 million and 15 million customers. And at that point, we should just be able to edit something and say, I need 100 of these, and you're good to go. So that is the requirements today from startups and mid-sized companies. But at the end of the day, we still need a single and kind of unified workflow to manage all of this. We don't want to use one tool for one cloud provider, the other tool for our bare metal stuff, or to manage GitHub or something. we still need a unified kind of workflow. And this is where Terraform comes in. So Terraform is our open source tool that ships with a single binary. So it's very similar to, let's say, Git. It doesn't have any server-side component. So you just download this binary, and you're good to go. So why did we even create Terraform, right? What was the motivation behind it? Yet another tool that you have to learn, right? So the idea here was to kind of have, we need to answer like few questions like, how do we provision resources which are different, like compute, network, and storage, which are completely different, but in a way that's consistent? How do we manage the life cycle of these resources? So we often think about creating stuff. We never think about destroying and deleting and updating them. We just like, oh, we need these things right now. And we forget about like all the other things that are part of the life cycle. So we wanted to focus on that in a way that's safe. And also wanted to kind of do some policy enforcement that developers should only be given access to a certain thing. Operators should only access this other thing and things like that. And the most important the question was, how do we automate and share these configuration files? We don't want to get into the whole like sharing Bash scripts and Python scripts. We wanted to kind of do it in a way that's like consistent, can scale with as your organization scales as well. When your application scales, you also add a bunch of more engineers that would come in and kind of work on the infrastructure with you. So Terraform's overarching goal is to provide a consistent and a unified workflow for using infrastructure as code. So the idea was to use all the things that we learned in software and apply that in infrastructure, and then do it in a way that we can safely iterate over like infrastructure from one stage to the other. And I'll kind of demo that in the next few slides. But also do it in a way that we are able to provision resources in any cloud provider. We don't want to be biased towards Microsoft or Amazon or anything else. We should be able to use the full, realize the power of the cloud, which is like to be multi-cloud or to run a certain application, certain cloud, because the pricing is better or something, right? So how do we do that? We do that using a very simple human-friendly language. It's called HCL, HashiCorp's configuration language. It's meant to be human-readable, It's like less known for its machine readability. But the idea here is that you have a resource, and you have a type of the thing, and you have the name for the thing, and then you have attributes. So how does that resonate in a real-life scenario? You would have something, let's say in this case, we are creating an Azure virtual machine, and the name is web, and then we have, we're providing that we need the Ubuntu server, the latest image, and things like that. And this is how we define an Azure image. Same way we can do the same thing for Amazon. In this case, I'm creating an Amazon instance with web, and Amazon uses AMIs or AMI or whatever group you belong to. I don't know, I call it AMI. But the idea here is to kind of take that AMI ID and create that instance using Amazon. You can do things which are super interesting. So in this case, we're going to mix and match. So what you can do is with Terraform, so let's say in this case, I've created a Azure VM, and I'm using a public IP to kind of expose that to the internet. And I'm specifying things like the location and things like that Azure needs to create this public IP. But I'm using DNS Simple as my DNS service. So in this case, what you can do is kind of cross-reference the resource's IP address when once available. And this is called interpolation in Terraform. So the idea here is that Terraform kind of creates a graph of dependencies of resources. So it in the background, like for you, you just define saying, oh, I need the IP address of this resource. Once this is available, make sure create a new DNS record called test. Terraform figures out that, I have to create the instance first, then create the DNS entry. And it does that automatically without you actually telling it. In a lot more other infrastructure as code tools, you have to say this resource depends on this other resource. I'm not going to name names, but you know which ones those are. But the idea here is to kind of have that defined implicitly. And then you can do this across anything. So you can have a CDN. You can create a Cloudflare page rule, or you can do a Fastly service if you wanted to. You can apply this for your GitHub organization, so to do user management in GitHub, even create GitLab projects if you wanted to. So one interesting use case would be that people that onboard in your organization, they can give you a pull request of saying, hey, create my user using code, and that's all audited, and you can go through the versions of it and things like that, and that would create their own user when they join the organization. So what does Terraform extend to? A lot of different things. So we have a lot of things. This couldn't fit in this page, so that's why there's and more. You can go to the site, terraform.io, to see what we kind of support. But there's over around 100 providers, including there's bunch created by the community and bunch that are managed by us. But all the major cloud providers are supported, and on-prem things like OpenStack and VMware, we support that as well. So you can do everything using Terraform on there. So what can be Terraform? This is another question that we get a lot of times. So anything that has a CRUD API. So basically, any API that implements create, read, update, and destroy kind of operations can be terraformed, and you can write a provider for it. So let's say you have some secret on-prem provisioning thing that you run internally. You can kind of create a Terraform provider for that, and then start writing code and share that with the organization. So with Terraform, you get this idea of describing your infrastructure in text files. So literally, what you describe is what you get. That is the idea with Terraform. And then you get a really simple human-friendly configuration. So when we came out with HCL, a lot of folks, the first feedback we got was that we want to generate our Terraform configs using a CLI tool or a templating engine or something. So immediately we realized that we should make HCL JSON compatible. So in this case, what you can do is HCL is 100% JSON compatible, so machines can generate and read JSON really well. So you can do that too if you wanted to. But for humans, we would recommend use HCL. It's better to write JSON. It gets crazy with nesting and stuff. Then you can store it in any VCS, right? So it's just text files. So you can use SVN, Git. If you're really really feeling lucky, you'd use Perforce. I don't know if you've used Perforce, but it's painful. And then you can track your history. So the idea is to kind of have an infrastructure repo. You go in, you see commits. So if someone onboards, you just share the repo with them. They can go through how the infrastructure has evolved over years, which is pretty awesome to see as well. So I'm only going to talk about a few high-level features of Terraform that are relevant, and rest you can kind of see on the Terraform docs. So Terraform has this idea of a plan and an apply, and these are two distinct stages of you going to get something out of Terraform. So the first one, I hope you can read this, is in this case, what we're doing is something actually a little bit more complex, but the idea is to kind of show how a plan works. So in this case, I'm doing the same thing. I have this virtual machine here, and Azure requires you to create a network interface and then use public and attach a public IP to that network interface, and then finally you get this whole thing kind of gives you a virtual machine with one DNS entry if you wanted to. And then here I'm again using that DNS simple, which has nothing to do with Azure. Azure has no idea about this DNS simple thing, but I'm doing the interpolation bit again. So here I'm referencing the IP address that would be generated using the public IP resource. So these are all interpolations, by the way. So these are all the interlinks between these resources. So now Terraform will, using graph theory, will kind of figure out okay, I need to create this this VM first or something, or the public IP first, and then attach it to the VM and things like that. And you don't have to do that. You just define it as you see it. Then you run Terraform plan, and plan is something really interesting. It shows you what will happen before it actually happens. And I said it right now, which is pretty cool. I can quote myself. So the idea is to kind of foresee changes. And before, we kind of didn't realize we could do that. Before, things were very much oh, I know that I've done this in the past, and it's a tribal knowledge that if I create this instance or change this IP, this will happen or something. But now you can actually see these changes. And the way you see these changes in this a very simple, plain kind of diff format, in which you see some pluses here. So these are all additions of you creating resources. And you'll see a bunch of output for each one. But I'm only expanding one of these just because there's not much screen space here. But here you see there's few things that are computed, which means Terraform doesn't know about the ID or the domain ID or the host name yet until this resource is actually created. Those are computed resources. REST things that it knows about, it'll show you right away. And it'll also show you that interpolation happening right here. So basically create the public IP first and then create the simple DNS entry. And then you can kind of share this plan. You can actually generate them and save them in a file and share that with let's say, an operator or a security person that understands what's going on, or some compliance reason you need approvals on something. So no more Jira tickets. You can kind of share that pull request and then get a +1 on it. And then you can go ahead and run Terraform apply. So how did we do this previously? When we didn't have this planning and applying phase separately, right? You just prayed, right? You just said, well, we'll see what happens, right? It was pretty much asking the other colleague is I'm going to delete this instance. is something going to happen? And they're going to be like, no, and then there's an outage. Like, this is always the case. Whenever you have to ask someone whether this something is good or not, you know this is something really bad, right? So in terms of like how does Terraform kind of track these resources, it uses something called the Terraform state. And this is kind of different from other like infrastructure as code tools. They don't really have a kind of database to kind of look things through. And there's a reason why we have a state file, which is separate. So basically, it kind of lets you map real-world resources with configuration. So you write the config. Once things are applied and things are like running, Terraform creates a state file, which is in a JSON format. And it kind of gives you the state of what Terraform left the resource at. Basically, so when Terraform runs plan again, or you do an update to a resource, Terraform can kind of diff what it has locally and kind of merge it with what the real world is, and kind of present you with that diff again in the plan format, and kind of give you what's going to happen the next time. So basically, the configuration is what you write, you define what you want, and the state is managed by Terraform. And this state looks like this. It's meant to be like not readable. It's pretty small, but like it's just a JSON thing. It has things like version and lineage, and it kind of gives you what depends on what and things like that. And it's kind of stored. It could be stored in a file if you wanted to. It could be stored in console, which is another one of our product. And then you can use it in Azure RM or S3 bucket or GCS or whatever else. There's a bunch of other backends that you can use. So the idea with kind of storing this state not in the local Git repo, but remotely, is that you can share this in your organization. So you can actually like share this like a state. Let's say your operations team creates a networking project in which like all your VPC networking is all defined there. And they can kind of share the state across, and then people can just include the state in their projects and use certain things like VPC IDs and like network interfaces and things like that out of that state, and it kind of makes it kind of scalable inside an organization. So at the end, what you get is this like really interesting dependency graph, which Terraform can generate for you if you want. And this is not meant to be, again, not meant to be readable. This is for the demo that you'll see today, which is kind of a bunch of things depending on each other. So here you see, just zooming into one like phase of the thing, you can kind of see like if we create a Google computer instance, the Route 53 DNS entry is kind of dependent on that. So basically, Terraform creates this first, and then once this is available, the DNS entry can be kind of consume that IP address of this instance. And there's other dependencies, as you can see across the graph. So this is what Terraform kind of creates. But you can actually generate this graph and like attach it as part of your project, and you can kind of see the infrastructure evolve, and it's pretty cool. So I want to also talk about collaboration, because in workflows, I feel like collaboration is something really important. And now some of you might be thinking, I'm going to say the D word. I'm not going to say the D word. So DevOps, no, I'm not going to do a DevOps talk here. But before anything existed, we had this wall, right? We had the developers on one side and operations on the other side, right? It was pretty much like siloed. And so developers were only focused on, software engineers were only focused on writing code. And operators were focused on keeping that code running in production, getting alerts for it. Basically, their life was consumed by this software that you wrote, right? And then once the software was ready, you throw it over the wall, which was like the term used, and then the operators would keep it alive. But then as kind of cloud kind of became a thing, software people realized that everything is now programmatic. Like you can actually use APIs to do things like create instances, change stuff, delete things, and things like that. And this became super interesting for them. They're like, oh, this is software, so I think we should be more interested. So at this point, that wall kind of slowly disappeared. And operators were really happy about this change because they want to kind of share that workload with someone else. And this is where you kind of saw like the software people move towards operations a little bit, and then the operations people moved towards the software people, and they collaborated. And this is where we kind of see DevOps exist or whatever. So how does that work in Terraform? So in Terraform, we use something called the modules. So the idea with modules is very similar to, let's say, a library in software. So you make a shareable like kind of code piece or code snippet that anyone can consume. So idea here is kind of like expose certain things that you need. So in this case, again, we have a similar example, actually the same example, in which what I'm doing is kind of making certain resources, certain attributes available for others to consume. So in this case, I'm going to make the count, the OS, and like the version of the OS, kind of consumable using variables. So what you can do is now, like any developer can kind of create like or write these few lines of code, and then source the module. In this case, the module is this one file. And then only specify the count, say like, oh, I need 10 servers, and specify the OS that they need, and that's it. And those are the only things that we take inputs to the module, and then you can kind of get a bunch of servers if you wanted to. And they don't understand the complexity behind, basically. So you hide the complexity. So this is how you get DevOps, I guess. So you have operators that know what they're doing in terms of infrastructure. I'm not saying software people don't. I shouldn't have said that. I take that back. So the operators, people that have interest in infrastructure and care about it a lot, because their job is to make sure everything is up and running, they can write these modules, and then software people can just consume it, and then you get a bunch of web servers, basically, and that's what they care about. Okay, so let's talk about what an end-to-end infrastructure cloud workflow, whatever, can look like with Terraform, and we'll do a demo for this. This is where you want the demo gods to be really, really kind. So for this demo, I'm going to use my special jacket that, since it's a live demo, hopefully this gives us luck, because live demos are really nerve-wracking. I don't know if you've done those, but they're pretty nerve-wracking. And then I'll try to make sure that that you can all see the terminal and stuff like that. And I'm going to use a conference Wi-Fi, so I'm really brave. So please don't do Docker poll right now. It'll be pretty bad. That's the worst. OK, let's see if I can find my mouse. I'll mirror my displays. Cool. OK. OK, let me know if you all can see it at the back. OK, cool. Thank you. So in this demo, we'll kind of go through a life cycle of using Terraform for a simple project, which is a multi-cloud project. And then kind of showcase some of the Git features that are available, which you can use right off the box, right out the box. And then kind of go through the modules workflow as well. So first, we have this simple project. I'll kind of just show you the Terraform config for it. I'll zoom in, don't worry. Yeah, so here what we have is a simple Terraform project in which I'm using Google and Azure in combination. So Google gives us the compute, and Azure will act as the DNS kind of authority or whatever. So in Terraform, the first thing you want to do is kind of define a provider, which is a cloud provider or the resource provider. In this case, I'm specifying Google to be one. And then you specify, in this case, I'm specifying some data resources. So this is something I didn't talk about. It's not that relevant for this demo. But with the data resources, these are read-only resources. So Google, Azure, Amazon, they can kind of give you a list of available Ubuntu images that they manage. So with this data resource, I'm just asking for Ubuntu 1604 images, basically. And then I'm going to use them later, and I'll show you how. And then I have a simple template script, which is another data resource, which kind of generates a script or a file for you if you wanted to. And I'm installing Nginx and simple web server things and stuff like that. And I'm sourcing few bash scripts. So this data resource kind of gives you something. I don't know if you're familiar with Cloud Init. So basically lets a server provision itself once it boots. So once the server is ready, it'll run the Cloud Init script, which will have install Nginx and make sure the index.html looks something like this or something. Basically, that's what this is. OK, so this is a good part. This is where the compute resources are defined. So here, I'm creating a Google Compute instance, and I'm specifying the name. And I'm making the count and app name and things just as variables, and these variables are available here. So the app name is here, and then the username and message and things like that, right? And then I'm defining some boot disk stuff, storage stuff, and then networking. I want a public-facing IP, and that's how we do it in Google. And then I'm making sure I have SSH keys so I can SSH in. I'm providing some IAM stuff to the actual instance. Then I'm creating the firewall rule. This is where the security comes in. Super secure, allow everything to the world, perfect. Super secure on port 82, as you can see. And then this is where the DNS part comes in. So here I'm, again, specifying the provider. In this case, the provider is Azure, a resource manager. And then I'm, again, doing something using the data resource to read a resource group. In Azure, I don't know if you're familiar, there's resource groups that are the top-level entity. And all the other resources fall under the resource group. And then I'm kind of also creating a DNS zone, which I pre-created, because DNS is not fun to work with in the real-life demo. And then what I'm doing is, this is the main part, which is I'm creating an A-name record. And I'm specifying the name of the record. I'm specifying the zone name. I'm referencing that data resource again. So the zone name comes from here, and the resource group name comes from here, right? And then the records. And here I'm referencing the Google resource. So I'm saying once the Google resource is ready, get the IP, and there might be multiple IPs if you wanted to, and then create a bunch of records for me, and that's it. And then I'm using output, which is another thing in Terraform, which you can kind of see after an apply. You can see a bunch of outputs, like the web server IP addresses, and like how to SSH to them, and like the web app address or something. It's pretty straightforward. So an app that runs an Nginx web server serves you some page, but is using a multi-cloud kind of strategy. So let me zoom out and go here. OK, so the first thing we do is Terraform init. This is a newer command that we created. This kind of downloads all the plugins and like all the modules. If you're using a module, it kind of downloads everything for you. So it sets up the, oh my God, this is taking too long. This is not good. It sets up the workspace for you, so you're up and running. Hopefully this doesn't take that long. Come on. Oh, I should have used my phone for tethering. Oh, almost there. Oh, there we go. OK. So this kind of initializes the workspace, right? Next thing we do is, as I said, run the plan, which will show us what's going to happen before it actually happens. And clearly, it won't work. Why does this not work? Module, the thing. Oh. OK. We are all going to get through this. Don't worry about it. OK, I have this. Not present provider. Or maybe, like, I need to do this. I'll try this again. What? I'm not sure what's happened here. Give me a second, sorry. OK, I'll move this module stuff out. OK. We will get through this, don't worry. Hopefully, this time it works. Come on. Come on. See, this is the thing. Even wearing this jacket doesn't do anything. When things go wrong, they just go wrong, right? We have enough time, though. OK, here we go. Plan. Please don't. Like, why? Module.webserver.data. OK, let's see what's happened here. Like, there's no module defined. OK, let me do one thing. I'm just going to move a bunch of this stuff in a new directory here. OK, templates, variables, web, env. And I'll move this to the new directory. I'm not sure what's wrong with this. This was just working before, like at the hotel room. Of course, it won't work now. Yeah, I don't know. I think this looks good to me. OK. Please. Oh, maybe. OK, well. I'll remove this. Last try. Otherwise, we'll move on. And it'll be unfortunate. This is the first time my lab demo hasn't worked. So I always see these speakers like, oh, like live demo failed? Great. And now I'm the one who's on the spot. So we'll see. We'll see if this works. Come on. Yeah, it's Azure, it's Microsoft. I know. I'm just saying. I agree with you. I think that's the provider. It requires like some environment variable to be present. I think it's something to do with the state. Okay, there we go. Okay, cool. See, we recovered, right? No problem. Now you can clap if you want to. We did recover. So yeah, there's a bunch of stuff that's being added here. Terraform tells you it's going to add like 6 different resources. It also tells you that it's going to create that Azure record. In cases when you'll update these things, you'll see a tilde sign which says updating, and then if you see a negative sign which is destroying, basically. So now we'll go ahead and apply, and hopefully this actually works. This is the part that's like supposed to break, but that didn't break. And in the new version of Terraform, you actually get the plan again, but you can say auto-approve, so you can actually just approve it if you want, but it's usually nice to kind of see the plan again. You can also save this plan in a file, as I said, and then use the plan, exactly that plan, to apply. So Terraform guarantees you that only that plan will apply, and nothing else will be applied to the actual like cloud provider or whatever. But the idea there is that if the upstream changes, so let's say someone went to the console and did something online, then that plan is no longer valid, and Terraform apply will fail. So you'll have to plan again to convert the state back to what it should be, basically. OK, so we got this state file. Now it's like locally stored. It's not stored in Azure, which was causing some problems, but whatever. So yeah, and now we have this domain name available. Remind me, never use DNS. OK, of course, don't use DNS for live demos. We'll just use a public IP. OK, not working. Oh, there we go. OK, so it's just booting up. And yeah, that's a web server, which is provisioned with like the Nginx stuff and things like that, and it's giving its name, and it's just like a hello world application. So that was like basically provisioning all that stuff. DNS is running in Azure. The DNS resource is created in Azure, and then the Google instance is here. And I can show you these things are real. Like I'm not faking these. So that's the DNS. That's the web server, and then the DNS record should be here somewhere. Let's see how long Azure takes to refresh. Oh, there we go. OK, so that's the DNS record right there. Right. So that's cool. Now, let's take a look at using modules, right? So what I'll do is I'll just move the modules directory, which I think is in 2 directory up now. Yeah, OK. Modules demo. And then we'll go to this modules directory. And I hope this doesn't have a state. I'll remove this. And then I'll also remove I don't know if the remote state will work for this. Let's just try. OK, so Terraform init. The remote state is basically like storing state in a bucket or something in Azure. But in this case, I'm just like, in the previous case, I removed that stanza because it was causing a problem. But again, we'll do init again. It'll basically download all the providers. So it locally caches most of the providers for the workspace. It's per workspace, basically. And then whatever is available, it uses that. And you can replace these if you wanted to. You can pin certain provider to a certain version. So you can do like graceful fallbacks and updates and things like that. So now we'll plan again, and hopefully this works. OK, so that's working. I'll just show you what's in the module. So if you open up the modules directory, so this could be something that the developer sees. So what they're seeing is basically these like 4 lines in which we're specifying the count and the app name. And that's it, right? And then you're specifying what the output is. That's it. So they don't realize, once they run plan, then they realize, oh, it's like a bunch of these things are actually inside, but they don't really care because they care about the software. That's it. So now what you can do is you can go ahead and apply. And then let's wait for this to be applied and make sure these instances are up. Come on. I should have like jokes prepared for this part, right? Like when there's like no one saying anything, it should be jokes. OK, there we go. So let's see if this instance is up. Let's refresh. Yeah, so I created 2 of these instances. The count was set to 2. And we have these 2 modules thing. And then let's just grab one of the IPs, because DNS doesn't work. They're still booting. Come on. Let's see the other one. All right, while they're booting, I'll start showing you the other workflow. So with Git, what you can do is kind of actually have an end-to-end workflow. So let's do this. Let's add this new directory or whatever that we created. So let's add, so git add, oh, actually, let's check out a new branch. This is normal Git workflow, so please bear with me. Let's say I need more servers. Git add, neuter, and then let's commit this in. Modules demo or something, right? Oh, has to be secure. Let's see if I miss my, OK, there we go. Worked on the first go. And then we'll push origin to the branch name. The branch name is this. You all might be thinking that he's teaching us how to use Git. I'm not. This is just me thinking. OK, now this pull request is ready, right? So we can create this new pull request. Now, this is the cool part of the demo, so hopefully this works. So now I have this thing ready. It has all my changes, so an operator can kind of go through what has happened. And then what they can do is, this might not work, but we'll see. Terraform plan. So we can say Terraform plan on the actual GitHub comment. And immediately what you can see is your CI/CD system can actually pick these web events up if you wanted to. And since Terraform is just this standalone binary, it can actually run in your CI/CD system, or you can write a web server that actually runs it and remotely run Terraform for you. And once it's done running Terraform, it can actually give you the plan in the GitHub pull request. So now what happens, you can share this link with an operator. They see the changes, right? They see what's going to happen in real life, which is the plan. They can go through it, right? And then they're good to go, and then they can say, in this case, let's say, we want to take it a step further. We are like, oh, the developers are like, no, I think we need 200. Or like, no, let's go with 20. Let's be a little bit more conservative and be like, I need more servers. And then commit this up. Yes, I didn't mean push. Oh, come on, Git. OK, and then we go here and we say Terraform plan. And now you can CI/CD system can kind of pick up the latest change that has happened, and then start running plan. Oh, hopefully this works again. I'm going to try again. Did it work? Sometimes Git's slow. Oh, maybe it didn't work. Let's try this again. Huh. Interesting. That should have worked. OK, whatever. It worked the one time, right? So we can. This is a stupid Jenkins instance running somewhere, but yeah. So you can actually go ahead and apply if you wanted to, and then the idea is to kind of get a +1 and get a thumbs up or something, and then go ahead and apply. Go ahead and apply basically right after that. I think I might have crashed the. OK, whatever. Yeah, so the idea is to kind of get a plus approval, go ahead and apply if you wanted to, and then you would see those instances appear here at some point, right? That's the idea. That's the end-to-end workflow. In this case, what I'm doing is kind of having the actual Terraform runner thing run on my laptop. So what was happening is I was invoking something from the web and was coming back to my laptop. So that's probably the reason why it's super slow. But that was the idea there. So that is the end-to-end workflow that you can achieve now. You can also do things like actually create graphs for your infrastructure. So you can run Terraform graph. Yeah, so you can run this command, Terraform graph. That kind of gives you a diagram of all the resources. And then, OK, whatever. I generated this. And then this kind of, OK, great. Great. Nothing is going to work today. Google, Azure, I think I was in the wrong directory. OK, graph. Cool. And then you can open up the graph. And then that's the graph that we saw earlier. And then you can actually do this. You can move this graph into your GitHub README, and then this could be part of the repo if you wanted to. So that's it in terms of what I had for you today. Yeah, thanks for coming to the talk. I have stickers for all our products, so you can grab those if you wanted to. That's also my job. You can ask me anything about any other product, HashiCorp product. Yeah, and then follow me on Twitter or like something. I'll make the slides available right after the talk, and then make the demo, the failed demo, available as well. So yeah, you can kind of consume that. Thank you. So any questions? Yes.
So we're using GitLab for CI/CD, and there they have the concept of a GitLab runner. Is there a Terraform runner for deploying to not accessible hosts?
Yeah, so there is a few open source projects that do, well, we have Terraform Enterprise, and it has integrations with GitLab and stuff, but that's like the part that you have to pay for. But I think you can get away with for a smaller organization with like for a group of 10, 15 people, you could probably use like just a simple like open source project, or you can even write like a simple runner. Because all you have to do is wrap Terraform around something. It could be a web server or something, and then just tell Terraform to run plan on a directory or something. That's it. And it's not like, and it's basically the actions that I did locally, you have to replicate them. And once you get an output, you just have to like do a REST call to GitLab and like push it back into the pull request. That is basically what it is. There's not much there. But if you need advanced features like IAM and like state management and like making sure there's only one apply going out at one time, then I would recommend using like Terraform Enterprise, and that it takes care of all that basically. It kind of helps you with collaboration there. Yes.
Where do you configure your subscription details? For example, your Azure subscription and your credentials.
So in this case, I don't want to show that, but like in this case, it's in the environment variable is the file that I was sourcing. But you can specify them in as part of variables too. So in your provider block, which I can show you, in the provider block. So let's open. I think it's in main. Oh no, it's in web. Oh yeah, here. So where is that? Yeah. So here. Oh man. Why? Okay, there. I can zoom in now. So here, this is empty right now because I was specifying all the variables that are required using environment variables, but you can specify them so that a user can enter them when you run plan as well if you wanted to. But the Terraform kind of inherits with what Azure defines. So if you're using like the Azure CLI and you're able to log in with the Azure CLI, then Terraform will use the credentials generated using the login. And so basically there's a hierarchy. The environment variables kind of take precedence over like the AZ CLI or something. But if you provide it using while running plan, then those are the variables that would take precedence. So there's a whole hierarchy that you can kind of follow there. Yes.
When I was looking at Terraform and Azure before, you had kind of a only infrastructure in mind, and it was basically like your demo here with DNS and VMs, but there wasn't a support for what Azure PaaS services basically. Has that improved?
Well, let's take a look right now. So we've actually we have a multi-year partnership with Microsoft. They work really closely with us. And so we've actually improved like the provider substantially since the last time I saw it personally. So here's the Azure provider. Let's zoom in. So those are just data resources, but like in terms of the base resources on the left, so we can keep going down the list. We have like some automation resources, insights, CDN, compute resources, Kubernetes if you wanted to. I had to use that word, boom. And then Cosmos DB, databases, data lake, DNS, key vault, load balancers. I can keep scrolling down the list, but we are only going to add to. So anything that Azure Resource Manager can do, Terraform can do, because we use the same Resource Manager APIs that are maintained by Microsoft. Yeah. Yes.
What's the main differentiator between Helm charts and Terraform?
So there's few differences. So Helm is only, Helm, for those of you who don't know, is the tool that kind of does templating in Kubernetes. So you can kind of template Kubernetes YAML files and things like that, only for Kubernetes, basically. So Terraform kind of targets, as I said, targets like pretty much anything. If you look at like the resource providers that we have, we target like anything from like CDNs to even GitHub, right? So if you go here, like these are all the providers that we kind of have available. And Kubernetes is one of them. I think there should be a Kubernetes provider, yeah. So it's something similar to Helm. But the idea here is to kind of have like that consistent plan and apply workflow for anything. And we really don't care whether you're deploying in Kubernetes or deploying a VM in Oracle Cloud or something, right? So that is the idea. With Helm, it's very focused to Kubernetes, and it tailors towards Kubernetes YAML files. And then in terms of differentiator, Helm has like the server-side component called Tiller that does like your deployment management, and it's very specific to Kubernetes again. Where else we don't focus on like being super specific to one, but we'll keep adding support to Terraform. On the other side, there's actually a Helm Terraform provider. So someone's written a Terraform provider for Helm in the community, and it's very popular. So you can actually use Terraform to kind of do those Helm charts as well and manage those charts as they go through the life cycle between creation and changing and things like that. So that's basically how we look at it versus Helm. I hope that's clear. Okay. Yes. Yes.
So before you would have to use Terraform to generate a Kubernetes cluster,
Mm-hmm.
and then use Helm to add things into the cluster.
Mm-hmm.
But now you can use Terraform for all of that.
Wow. You know what? Can I record what you just said and like show it to my team? Because this is what we've been trying to talk about for a while. But yeah, you can do that if you wanted to. So like I don't think there's any harm in like kind of doing them separately if you wanted to. But like if you want the same HCL language, which is pretty human readable rather than reading YAML, then you can do that for sure. But in terms of the Kubernetes provider, there's only a few stable resources that we kind of support right now. So there's only these things we support right now. But in the future, this is only going to grow as things become stable in Kubernetes and get merged. This provider is only going to like we're going to focus like a lot on the Kubernetes provider because the community, there's a lot of overlap. A lot of Terraform users are using maintaining Kubernetes clusters and deploying stuff to it. So, and then as I said, you can kind of transition just using the Helm provider. So you can kind of start using the Helm provider, using Terraform, and you can still maintain your Helm charts, and then kind of get used to the Terraform workflow. And if you like it, then you can move on to actually fully using the Kubernetes provider if you wanted to. So yeah, both. I don't advocate for one to the other, but if you want consistency, then I think that's like the way to go. Yes. Yeah, so the idea is to kind of, it's funny you said like drifts and drift management and things like that. So I think this is literally the post that just came out. One of the newer members of my team wrote this post. So the idea is to kind of use the state file to detect drifts. So you can have like a cron job or like some Jenkins system that runs periodically and then kind of does this diff for you. And if it sees any changes in the plan, then it kind of reports you or something and things like that. So Terraform itself cannot invoke itself, basically. You still need like something like Jenkins or cron job or something to invoke it, but you can for sure do the drift detection. And I think you should go through this post. It kind of breaks everything down really well in terms of what is required on the state and how does refresh work. And then in terms of reconciling state, like how can you kind of do that, basically. That is the post. And it's perfect timing. My teammate's going to be happy. Yes?
So let's say I'm using Terraform to manage two cloud providers, same resources, two cloud providers, and I do one cloud provider, and when I switch to the second cloud provider to spread the resources, it fails. What's the rollback strategy for the first cloud provider, if there is any?
Okay, so in this case, what will happen is if there's a failed apply, so let's say it was able to, like, it was like a partial apply. So if Terraform was able to successfully create a Google instance and wasn't able to create the Azure VM or something, I'm not saying Azure is bad, but just being clear. So if that happens, then what you're going to do is like, if you want to roll back, you can kind of taint a resource. So I didn't show you, there's another command called Terraform destroy. So that you can target resources. So you can say like Terraform destroy this one resource and only target that one resource and basically destroy it and remove it from its like state as well. And so you can do that. That is basically the rollback strategy at that point. So you'll have to destroy the older one and the partial apply just remains as it is. Then you can replan to figure out whether that instance was actually not created or there was some upstream API error or something. So the plan will kind of show you, the next time you run plan, it'll kind of show you what the state of that resource is in real life, basically. Yes, it doesn't happen automatically, yeah. So Terraform it's very optimistic, so it'll try to apply as much as possible. So it actually parallelizes the operations. So if 10 resources can be created independently, they'll be created right away in a more parallel fashion. But if there was something interlinked, like the demo that I had, in which like we were you know the demo, but like it was being, we were referencing few things. So Terraform will do them in a sequential manner, make sure like everything is created first before using them. So yeah, that is the idea. There is no like automatic rollback.
And how do you verify success?
So if an apply is, once the apply finishes, you'll see a success message, hopefully. If it was successful, hopefully we have a success message here. Yeah, so you'll see apply completed. It'll give you an error code back.
What I meant was, in a series of operations,
Yeah.
like, would you proceed if some steps fail?
No, then, like at the end, if any one of the steps fails, the whole plan is supposed to be failed. So like the whole thing will fail. And you'll see an error there, what failed and what was successful. But at the end, the error code would be failed. So yeah, that is the idea. So it's not like, okay, like one was successful and the rest failed, but you're still going to show success. That's not the case. Yeah. Cool. Thank you. I think that's my time. Thank you. Thanks a lot.